Okay, so welcome everybody to the Joint Israeli Probability Seminar. And we're very happy today to have Fabio Toninelli from the Technische Universität Vienna to tell us about logarithmic super-diffusivity for two-dimensional out-of-equilibrium systems. Thank you, Fabio.
Thanks, Ron. Thanks for the invitation. Right, so I would like to tell you about a couple of projects in collaboration with G Cannizzaro in Warwick, Erhard in Bahia, and my PhD student Levi Haunschmid in Vienna. So feel free to stop me anytime. So I also have a part where I would like to give some ideas of the proof, but it's actually perfectly okay if we skip that part and we rather focus on the results and the model. So that's perfectly okay. So right, so the plan would be to first give the context, what is the problems we would like to understand, etc., in a kind of broader context than what I will later focus on. Then we will see two probabilistic objects. One is a diffusion. It's a diffusion in the curl of the two-dimensional Gaussian free field. The second one will be a variant of the KPZ equation in 2 dimensions. And then, okay, I will come to the results about this super diffusivity. Somehow these models are both in okay, you are used to mode like statistical mechanics models where according to the dimension, you have a different critical behavior. And then usually there is some critical dimension where which separates dimension where, like in easy model would be dimension 4, a case where behavior is Gaussian from dimensions where the behavior is non-Gaussian, and then there is a critical dimension in between. So for these models, it turns out the dimension, this critical dimension is not 4 like for easing, but 2. Okay, and then maybe some ideas of the proof. All right, so let's see the first example, which is not an example, and it's not a model where I have any new results to tell you about, but it's just it's something relatively well known, very well known even. So I start from that. And that is the asymmetric simple exclusion process. So this is ASEP. So it's we're on ZD, we're on the lattice ZD, infinite lattice. It's just a box of ZD that I have here. On this lattice, there are particles, at most one per side, and these particles jump around. Let's say they make nearest neighbor jumps in continuous time. So it's this Markov jump process. And the transition rates, I would call the jump transition. Okay, each particle jumps from a position, say the origin, to a neighbor of the origin or to a neighbor of the position where it is, with the rate that is just depends on the translation invariance. So if I start from the origin, I jump to X, the transition rate will be called Px. Obviously, the rates sum to 1. And there is the exclusion rule. You see here that you cannot jump on a particle that is already there. So the jumps, when you try to jump on a particle, then the jump is just disregarded. And in general, we look at the situation where the jumps are asymmetric. The average of the position after the jump, if you want, is not 0. Okay, so gamma, let's call gamma the asymmetry. Gamma would be a vector in ZD. It's somehow the expected value of the position after one jump, if disregarding the exclusion. Okay, you can see this as biased random walks with exclusion rule. Okay, so this is the simple exclusion process that you can consider on any ZD, actually on any graph you like. Now, a very well-known fact is that if you start your process from a product of Bernoulli measures, so on each side you put particle or a particle with probability rho independently on every side, then these measures are stationary for the dynamics. I call them mu rho, but actually I think this notation will not appear anywhere later. So now, so stationary processes are actually very easy and actually don't depend on the asymmetry parameter. But the question one would like to understand is not what happens at a given time, but somehow how the space-time process behaves on large scales, especially whether it is diffusive on large scales. So for instance, if you follow a single particle Will it essentially diffuse like a simple random walk, maybe with some up to some drift? So in general we have a drift, but once you subtract the drift, is this behavior diffusive?
Sorry,
okay. Yes.
Rho can be any number?
Yeah, rho can be any number between 0 and 1, yes.
Thank you.
Yeah, so irrespective of gamma, all the Bernoulli rho are stationary. They are not reversible. They are reversible only if there is no drift, but yes. Okay, so one way to measure diffusivity is through the so-called bulk diffusivity coefficient. So let's see how it is defined. So suppose you take a sum over ZD of, you take the correlation. Okay, so let's call eta xt the indicator function that there is a particle at x at time t. Then you take this semicolon means I'm looking at the covariance between these two things at xt and at 0, 0. I'm taking this covariance under the measure of the stationary process. So I start from mu rho and I let evolve. I look at this covariance and I sum over x, this covariance times x squared and divide by t. Okay, so what so if there is no drift, then this covariance behaves like the heat kernel. So it behaves like for large times, let's say, behaves like a Gaussian of variance t. Okay, in the dimensions. Okay, so this is
you mean if there is no exclusion, not if there is no drift?
No, but even with this, okay, so if there is no exclusion, then it's just a single particle. But even for the exclusion, for the symmetric exclusion, this is the large scale behavior. I mean, it's not obvious, but this is yeah. So if you believe this, then without exclusion, then this sum is essentially of order 1 because you're computing the variance of the Gaussian and dividing by t. Okay, so for large times, this is essentially a constant. And actually, so this quantity debulk is essentially measuring how correlations grow in time. So this behavior here is telling you essentially that this correlation becomes 0 when at distances of order square root t. Okay. And then it has this behavior. Okay, I see there is a question on the chat. Yes, this is this holds when you start a Bernoulli. Yes, in this expectation, when I put this row on top, the bottom right, it means I start from the this is expectation with respect to the stationary process. So it starts from mu rho, and then stays mu rho at all times. But I don't just write expectation mu rho because this is expectation of according to the law of the process. It's not just an expectation at given time, but yes. So this is when you start a new rho. Okay, so so this tells you that essentially that correlation length grows like square root of t. It's a way to, but somehow it's convenient to look at this debulk because it's already summed over space. It's a single number and not a function. Okay, so then the question is, so this is when there is no drift. And then what happens when there is a drift? When this is by now well known, in dimension 1, this bulk diffusion coefficient diverges for t large, diverges like t to the power 1/3. This 1/3 is the exponent of one-dimensional KPZ equation. Here I'm being very sloppy with the literature, but for instance, okay, so here I cite a work by Ballas, Castell, and Selfpropelling, but actually there is much more than this. So for one dimension, it's well known that there is a super diffusivity. So this is indicating somehow that okay, what it means essentially is that this correlation is still non-zero even for x's that are much larger than square root of t. Somehow the correlation length grows much faster than square root of t. In this sense, the system is super diffusive. Okay. In dimension higher equal to 3 or higher, again, one finds the usual a diffusive behavior. So this diffusion coefficient for large times is of order constant. It can depend on rho, it can depend on gamma, but is of order 1. And there is a series of papers by Landim, Olla, Yao, Varadan, and others about this. And the critical dimension is dimension 2, where you start seeing some corrections with respect to the diffusive behavior, but there are somehow marginal corrections. They are logarithmic, and these corrections are of log to the power 2 over 3 order that were conjectured by Van Beeren, Kuttner, and Spohn in the 80s, and then proved 20 years later by H.T. Yao. Okay, so this is was just to introduce the type of phenomena we look at. Simple exclusion will not appear in the rest, but if there are any questions about these 2 slides, you should ask now, because ASEP then will disappear forever somehow. Okay, so the thing to summarize. So summarize here, we have a system. You may think of interacting diffusion. This simple random walks that jump. You put a drift, and then we wonder whether the system remains diffusive or not, and this will depend on dimension. In low dimension, not. In high dimension, yes, and there is a critical dimension where you already see some non-trivial corrections, but they are just of log to some power here, 2/3 order. Okay.
Is the 2-dimensional model also a little integrable? How do you get such results?
No, there is. I mean, at given times, as you see, the stationary measure is totally explicit, but there is no integrability in time. There is nothing like in dimension 1.
Right.
No determinantal formulas.
Right. Very impressive.
Yeah. So it's really, yeah. No. The answer is no. There is no.
Yes. Okay. Thank you.
Welcome. Okay, so there are other systems where this type of some logarithmic corrections to diffusivity are predicted, especially in 2 dimensions. One case is 2-dimensional fluid. So think of, for instance, a system of hard disks, say at equilibrium at some temperature, and then you follow one disk, one tracer. And then it is conjectured that if you look at the mean square displacement of this guy, it will be of order t times square root of log t. This is somehow there are arguments, theoretical arguments, but there is no proof of this. There are proofs of much weaker super diffusivity of order log t for certain gas models on the lattice by Landim, Ramirez, Yao. But this is for a tracer particle in hard disks in dimension 2. This super diffusivity has been conjectured in the 70s.
And this does not require asymmetry. This is also in the symmetric case of the diffusion.
This is symmetric, yes.
It's a bit different.
Yeah, but the yeah, you're right. It's yeah. So yes. Another case where this has been corrections of this type have been conjectured is so-called self-repelling Brownian polymers. Let me try to explain this with just a picture. So imagine you are in dimension 2. And you consider something like a polymer, and that evolves in time. And the way it evolves, the position at time t is called xt. The way it evolves is there is a Brownian term, so there is a Brownian diffusion dBt, but then there is a drift, and this drift, this minus grad lt xt, just means that the position of this guy has a drift, and the direction of the drift is minus the gradient of the local time. So you try what it means is that you try to go away from the positions which you have visited in the past. So you look at the position, you look at somehow the time you have visited your several points, and you follow the direction of minus the gradient. So you try to move away from the points where you have visited most. Okay, so this is called actually it's called this in the physics literature is called the true self-avoiding warp for some reason. But anyway, so it's defined by this stochastic differential equation. And again, if you look at the mean square displacement divided by t, it is conjectured to grow like log to some power alpha. Alpha is most likely 1/2, but again, there are very much weaker results proven between log and log. Okay, so yeah. Also here there is somehow a rotational symmetry. Okay, oops, I'm sorry. All right, so notice that in the ASEP case, we had the log to the power 2/3. Here, at least in the conjecture, the power 1/2. This is, in fact, in this business of log corrections for interacting diffusions, there are actually two universality classes. There are really, okay, it will be not obvious to see, but yeah, actually, in fact, this is related to this symmetry versus asymmetry. For the ASEP, you have really a preferred direction. And while for these other two other examples in this page, there is more isotropy of the model. And in fact, this is responsible for the different exponent in the log. Yeah, so actually, I'm coming back to your question.
But we said that in the symmetric case.
Yeah, in the symmetric. Yeah, but in the symmetric. Yeah, but the symmetric case is different because it's actually a reversible dynamics. So in that case, not only it's isotropic, is really a reversible dynamics. This is the big difference. In all the cases that are also in this page are somehow it will be more evident for the cases for which I will tell you theorems. They are all there is still somehow a rotational symmetry, but time reversal is not true. This is a big difference with respect to simple exclusion, symmetric simple exclusion.
Okay. So in this case, the drift becomes so the drift away from the origin becomes weaker as time progresses with the correct scaling. This why you get the 1/2.
If, for instance, this self-repelling Brown problem, so the average position will be 0, so there is no net drift. For instance, for this self-repelling Brownian polymer, there is no preferred direction. So on average, you don't move away. It's really the mean square displacement. But actually, okay.
It's 0 because of the rotational invariance, right? But if you look at the distance from the origin, there should be a drift, right? Going away from the.
You mean the absolute value?
Sure. I mean, you get 0 because of the vector symmetry, right? But
yes,
you will have a drift away from the origin in a circular direction, I guess, right?
I mean, if I look at the expectation of the absolute value of x.
Exactly. But then,
then that would be of order square root of t times log to the 1/4.
Then, unlike the previous case where you have a constant drift, here it should somehow decay as it spreads out, and this is.
Yes, if you want. So that's for sure. But yes. But one should not somehow try to push the analogy between the two too much, actually.
Okay, thanks.
But yes, that's the case. Okay, so these were more or less the introduction. I see I already used 20 minutes, but it's okay. So let me come to the two models for which we have new results. The first one is a Brownian diffusion in the curl of the Gaussian free field. So let's see what it is. Xt is you have to see as a position of the particle on the plane. So it has two components, x1, x2, and it evolves according to a stochastic differential equation that is here. It starts at 0. There is a diffusion part, dBt, is a standard Brownian motion, two-dimensional. And then there is a drift part, omega, depending on the position, times dt. This omega is a time-independent random vector field, has two components, and has some distribution, some law p. Okay, so there is a Brownian randomness and there is a quench randomness of the environment. Now, the name of this model comes from the fact that this omega is taken to be is related to a Gaussian free field in two dimensions as follows. So you take psi to be a Gaussian free field on the plane. We will regularize it in a second, but for the moment, think of just a Gaussian free field. And then omega 1 and omega 2 are related to the space derivative of the field, like as written here. Omega 1 is the derivative of psi in direction 2, and omega 2 is minus the derivative of psi in direction 1. So written in vector notation, omega would be the curl of the scalar field in 2 dimensions. Okay, so well, as you probably all know, so the Gaussian free field on the plane is not a function, is a distribution. I can still differentiate it in as a distribution, but I would like here to have something smooth. So what we do is you start from the usual Gaussian free field not regularized, which is this thing with the tilde. It's a Gaussian distribution on the plane of average 0, and such that once you test against the test function phi, you get a normal a Gaussian random variable of expectation 0 and variance the h-1 norm of phi. So the covariance of this field is simply the inverse of the Laplacian on the plane. Okay, and then we simply convolve this Gaussian free field with some smooth function u in space. U is kind of bump function, which is rotational invariant, smooth, and everything. And then our Gaussian field loses the tilde, and you have something smooth. Okay, so this is
well, but in dimension 2, there is no Gaussian free field without mass with this correlation. It's impossible to do it.
What do you mean? Because of the you mean because of the additive constant?
Yes, constant.
Yes, but here actually we are taking the derivative. So actually yeah, you're right. So a priori there is an undefined infinite constant, but we just take the derivative, so everything is well defined.
Okay.
Yeah, thanks. Okay, so psi is this regularized field, and now omega is perfectly smooth vector field, pointwise defined and everything. Yeah. Good. So this is the equation. The question is, how does this oh, I see there are questions in the chat, so I don't regularly look blah blah blah. The Gaussian, yes, the Gaussian free field is fixed once and for all. Yeah, once and for all, but in a moment we will take joint expectation with respect to Brownian and GFF. But anyway, yes, there are 2 independent randomness. So the question is how this object behaves for large T. Does it diffuse or super diffuse? And the conjecture that actually this model was introduced by Balintot and Benedek Valco in like 10 years ago. And they conjecture that if you look at the joint expectation with respect to Brownian and environment disorder, so this would be called the quenched average expectation, the mean square displacement is of order T times square root log T. Again, if you don't put the absolute value and just look at the expectation of the position, this is 0 by symmetry. But we're looking at the mean square displacement.
Fabio, how to think of a walk in a curl? So when you're in a like saddle point, how should the Gaussian free field look like to push you in a certain direction?
Yeah. So that is I think it will. Okay. Oh, where is it?
Okay,
yes.
I can wait.
Slides. I will say something. Yes.
Thank you.
Yes. All right. So yes. An observation is that is actually, since I will not manage to go to the proof, so let me make this remark now. It's important if you look at the definition of this field omega, of this vector field omega, you will see that pointwise it has divergence 0. I mean, it's a curl. So because it's divergence 0 and because its law is ergodic, it's well known that the measure of this environment is stationary. So what I mean is that you start at 0 and then you move around. If at every point you recenter your environment at the position of the particle and look at this so-called environment process, then at all times the law of the environment process is the same as initially. So the law of this. Yeah, this law P is stationary for the environment process, and this is related to the consequence of divergence-free plus ergodic plus being ergodic. If it were not a divergence-free, in general, the law of the environment would change with time, but here it doesn't. Okay, good. So yeah, so come. Okay, I don't have a picture, but what you, yeah. Actually, this is not a heuristics for the conjecture, because actually I have no heuristics for this square root log t, but just would like to answer Ron's question. So if you look at the equation, you have two effects. One is the diffusion part. One is this driving force. Now, what you can see immediately is that the drift, the driving force, is tangent to the level lines of the Gaussian free field. I mean, it's this thing here is orthogonal to the gradient of the field. So you should imagine that you have, I don't know, you have Gaussian free field smoothed in space. You look at its level lines. And then the drift part will tend to just push you along. I mean, you would stay along the level lines if you had only the drift omega, while the Brownian part will tend to move you away. So now, okay. So, but somehow this field is true. It's parallel to the level lines, but it's not constant. So you move faster when you are at places where the gradient in the orthogonal direction is very high. So you move along the level lines, but not at constant speed. If you had only omega, then plus there is the diffusion. Okay, so I don't know if it answers the question, but there is really some non-trivial interplay between motion along level lines and diffusion. So there are some works in the past. I mean, it has been known for some time that having a divergence, adding a divergence-free drift to a diffusion can enhance diffusivity. So there are cases where it's known that you start from a diffusion, a normal diffusion, you add certain type of random divergence-free field, and then the particle can become super diffusive. I mean, this I mentioned here this work by Fan Yang and Papa Nicolaou, which, I mean, doesn't cover our case, but just as an example of a case like this. Now, for our particular model, I don't think it's proven anywhere, but one can heuristically argue that these level lines of this field are finite, but actually quite long. So they have very long tails. If you look at the probability that the level lines going through the origin is at least of length L, this decays slowly with L. So somehow you have to think that you have these very long level lines. Maybe the heuristic is that you move along these very long level lines, and then thanks to the diffusion, instead of staying on these closed circuits, you move to even longer ones, and then this provokes this super diffusion. I mean, as you see, I put a question mark on heuristics because it doesn't really explain the square root log t, but it indicates there is some non-trivial interplay between level lines and diffusion. Okay, so let's see what is known. What was one known? Well, in the same paper where Todt and Valco gave the conjecture, they also proved that super-diffusivity in fact holds. So they had a lower bound of order log t on the mean square displacement divided by t, and an upper bound of order log t. And in this business, actually, it's convenient for reasons that maybe I will manage to explain. It's convenient not to work in real time, so to speak, but in Laplace transform. So it's better to look at the Laplace transform of the mean square displacement. And actually, so let's call it d of lambda. And actually what they prove is that for lambda going to 0, this d of lambda diverges like lambda to the -2, which would be the thing you would have if the mean square displacement were just t, times a correction that is at most log lambda and at least log lambda. So if you translate to real time, you think that the real time t corresponds to lambda equal 1/t. This corresponds to the thing in blue, but actually what they prove is the thing in black. Okay, and then the conjecture in Laplace transform would be that if you take d of lambda multiplied by lambda squared divided by square root of log lambda, then this should be of order 1 as lambda goes to 0. Okay, so let me, if there is, I don't see any question on the chat. So, okay, so this is what we prove is essentially the conjecture up to log logs. So yeah, this is a paper with Giuseppe and my student Levi. We have that this ratio that should be of order 1 as lambda goes to 0. We prove it to be at most of order log of lambda. So it's still we cannot pin it down to a constant, even to order 1, but somehow we identify the leading correction, the leading order, which is square root of log, and then we are left with these logs, which are most likely just an effect of the proof. All right, so this is what we prove, and if you prefer real time with respect to the Laplace transform parameter, for upper bound this is no problem. It's easy using an argument by Castello and Valco to translate this in real time to get exactly what you could imagine, that the mean square displacement is at most t square root t log to the power whatever. And for the lower bound, well, you cannot directly deduce something, but you can, for instance, some weak statement is also okay. Some limb soup. I mean, the statement like written here, for instance, holds. Well, which is already. I mean, it shows that actually, certainly this process is not. The mean square displacement is actually has this square root log t correction. Okay, so let's see. Yes, this is yes. So this was the model 1, the example 1, where we are able to prove this square root log t corrections. I suggest if there are questions about this, ask now, because now I would introduce the second one. The second one is the so-called anisotropic KPZ equation in 2 dimensions. So probably most likely you have seen the KPZ equation before, I guess. So let me give right away the equation. So it's a stochastic PDE in 2 dimensions. So the unknown is a function h of space and time. Space is 2-dimensional, time is time. And then the equation looks like this. It's a nonlinear SPDE. You have a time derivative of h equals, well, Laplacian, okay. Psi is a space-time white noise. And then the nonlinearity, in the usual KPZ equation, the nonlinearity would simply be some coefficient, say lambda, times the square of the gradient of the function. Here instead, in this variant of the KPZ equation, you don't have the square of the gradient, because we have this combination of squares of derivatives, but with a minus sign in between, which is important. So the usual KPZ equation in 2 dimensions would be obtained with a plus sign, and there is no way of transforming one into the other with some trick. It's just really two extremely different equations. Okay, so this is the equation. Actually, to make it well defined, as usual, one regularizes the noise. You can either take the noise, smooth it out in space as we did for the previous equation, or you can regularize the nonlinearity in Fourier space. Okay, let me not enter the details. Actually, what we do is rather the second option, but okay, at this level of detail, it doesn't matter. Okay, so question is, how does this equation behave on large scales? Is it diffusive or super diffusive? And what is well known is that if you drop the nonlinearity, so if you put lambda equals 0, well, now we have a linear equation. It's just a stochastic heat equation with additive noise, and this behaves diffusively. So if you rescale diffusively space and time, the law of the process is invariant when lambda is 0. So this is something well known and actually easy to see because of the scaling properties. Well, this is true if you don't put the regularization. So if you put the white noise in space-time and you have just a Laplacian, then the equation is exactly scale invariant under diffusive scaling. And then what happens when you have the nonlinearity? Now, what is the advantage of having this minus sign in the equation is because of this first remark here, is that in this case, if you start your equation from the, oh, I see there is a question. What means up to log? Yeah, yes, what I meant, okay, so this refers to the theorem. Yes, no, I mean that if you go back to the conjecture here, we instead of proving that this, essentially, instead of saying that d of lambda times lambda squared behaves like square root log, which is the conjecture, we have it that it behaves like this times something that is at most log and at least 1 over log. Yeah, so I hope it's clear. This is what I meant.
Thank you.
Up to a multiplicative log if you want. Is okay? Okay.
Thank you.
Yeah. Yes. So this is important. So thanks to this minus sign in the equation, it's not a trivial fact, but one can check that if you start your initial state from a Gaussian free field in the plane, say, okay, forget about the infinite constant. So we could look at the gradient of the equation, but if you start from the Gaussian free field, it stays stationary. The law of the Gaussian free field is stationary, which is not the case if for the usual KPZ equation. In that case, you can check it's not stationary, but if you put this minus sign, that it is. There is some cancellation, which makes the Gaussian free field stationary, but not reversible. For the linear equation, the Gaussian free field is, law of the Gaussian free field is stationary and reversible. With the nonlinearity, it's not reversible anymore. Okay, and then I've written here that for the linear equation, if you rescale space and time diffusively as here, then this process here, scaled like this, has a law that is independent of epsilon. Okay, so let me see what we can prove. Okay, I will give a very informal statement of the result. Actually, it's a bit, it's extremely informal, but hopefully readable. What we do, what you can do is you take this equation, look at the solution, rescale it diffusively. So I get something that I call H epsilon of x and t. And now the question is whether this is at least asymptotically as epsilon goes to 0, whether this is scale invariant. So the linear equation is exactly scale invariant, and here we might hope that at least asymptotically as epsilon goes to 0, this is scale invariant. A way to look at this is to test this solution against a test function phi. So okay, you integrate in space, you get something that I call H epsilon t of phi. And then the very informal statement of our result is that as soon as you have the nonlinearity, this random variable H epsilon t of phi and the same thing at 0 become essentially decorrelated as soon as t is of order 1 over square root of log of epsilon. So remember, for the linear equation, the law of the process does not depend on epsilon. So these two things will decorrelate, but at time of order 1, because epsilon doesn't appear in the law of the process. They will decorrelate, I don't know. But here, as soon as you put the nonlinearity, the two things decorrelate almost immediately in a sense. I mean, on scales of order 1 over square root epsilon. And so it means that the diffusive rescaling is not the correct one asymptotically. You have to rescale time a little bit slower if you want to hope to get to some limit for the process, for instance. Okay, so this again is an indication that there is some super diffusivity. The system evolves faster than the linear equation. Yeah. So this is okay. Actually, what we prove is a bit different, but now you might ask, what is the relation between these two models? We have a diffusion in a random field, and we have this SPD. In which sense are they similar? So let's rewrite the two equations in an integrated way. So they were written as differential equations. Let's integrate in time. And then, well, like for instance, the diffusion, you just integrate from time t0 to t. So the position xt is equal to b of t plus the integral from 0 to t of the drift computed at xs. I mean, nothing happened here. Similarly, for the KPZ equation, you integrate from time 0 to time t, and then you get, I mean, the initial condition h0 of phi plus the integral from 0 to t of the linear part plus the integral from 0 to t of the nonlinear part. Okay, so nothing happened here. Now, let's just call for to unify notations v of t, the thing that is in the integral. In one case, it will be the drift. In one case, it will be the nonlinearity. Now, what does it mean? Okay, so look at, for instance, at this first equation, at this first case here, where here. So we are asking whether the process is diffusive or not, whether the mean square displacement is diffusive or not. So of course, the BT part is diffusive, it's just a Brownian motion. So the question is whether the second part here is much bigger or not than the Brownian part. So so this is to say that if the variance of this blue part is much larger than t, then you have superdiffusivity. At least in terms of, yeah. For this first equation is obvious. For the second one, you have to, okay, one has to think a little bit, but it's also the case. And so what matters is to study. So first indication is to look at the variance of this blue part. I mean, this actually the point is to evaluate the variance of this integral. And now there is a classical inequality, a classical estimate that tells you that the variance with respect to the stationary process, P is well, okay, so P would be the law of the stationary process of this integral is divided by t is upper bounded by the expectation of, you have to take v, this observable v, times you have to take the okay, so let's read it. There is the inverse of 1 over t minus L0, and then times again v. Okay, what is this stuff? What is L0? L0, it is the symmetric part of the generator of the process. And well, 1 over t is just 1 over t. So L, for the diffusion, L would be the generator of the environment process, the Markov process that gives you how the environment seen from the particle evolves. It has it's a Markov process. It has a generator L. You take the symmetric part. It's as I told you that process is not reversible. So this generator is not symmetric. You symmetrize. The symmetrization you call L0, and then you compute this this expectation involving the inverse of the symmetric part of the generator. Okay, I mean, this is an inequality. If you know it, good. Otherwise, believe me. And now it's only an upper bound. It's an upper bound. It's not necessarily asymptotically equal, or even as an order of magnitude. It's an upper bound. But now one can compute this expectation because the stationary measure is Gaussian. So believe me, one can compute this thing. And it turns out that for both models, this expectation is of the form of an integral over momentum space. You can go in Fourier space, and then you get an integral dp of essentially 1 over p squared plus 1 over t. Okay. I mean, this requires a computation. But what turns out is that so this integral is singular near the origin if t were infinite. But and since we're in dimension 2, you can compute this integral diverges in t as a log t. If the same thing were in dimension 3 and higher, you would have something convergent even for t equal infinity. But in dimension 2, this is logarithmically divergent, and you find the same logarithmic divergence in both models. I mean, the integral is a bit different, but of the same type. And this is what makes the two models, in a sense, similar. Okay. Now, this is just an upper bound. It tells you, and actually, this is the way one can prove that the superdiffusivity is at most over the log t. But what the conjecture is actually the square root of log t that you don't see from this computation. Okay. Just as a remark in terms of literature, we have this diffusion in this divergence-free vector field. this is not, there are a lot of literature on diffusions in divergence-free ergodic random fields, vector fields. And in cases where the vector field is such that this integral, the analog of this integral would be finite, then this is called the so-called H-1 condition. And then it is known that in those cases, the behavior of the model is of the particle is diffusive. There are works by, for instance, Komorowski-Olla in the continuous setting and by Kozma taught in the random walk setting that when the analog of this integral is finite even for t equal infinity, then the behavior of the particle is diffusive. There is even a quench CLT and stuff like that. But here we are really at the boundary, at the critical dimension where this integral barely diverges. Okay, so let's see. Because this is where the idea of the proof would start, but it's I don't know if it makes sense to. How long should I leave for
well,
questions?
you still have about 10 minutes, even 13 minutes. I think you
okay.
should,
okay, I can try to give at least an idea. So, right. So let's for simplicity, let's restrict to the diffusion in the curl of the Gaussian field, of the Gaussian free field. As I said, the important object to look at is the environment seen from the particle, omega, let me call it t, omega t, which is simply recentered from with respect to the position of xt. And the law of this process, P is the law of the environment is stationary for this environment process. Okay, so this environment evolves as a Markov process. It has some generator L. It's not reversible. So we can decompose its generator into a symmetric part with respect to the low P and an antisymmetric part A. And I mean, of course, you can write A as some A plus minus its adjoint. I mean, this is nothing. It's just empty statement. But what is not empty is okay. So this is just L is the generator of the process, and then the step 0 of the proof is to, this was something already well known, is that well, remember what we care about is this integral here. We want to understand whether this integral here, where phi is simply the, okay, here we are looking at the first coordinate of our tracer particle. Just by symmetry, we look at the first coordinate at time t equals b1 first, okay, bt coordinate 1 plus the integral from 0 to t of the first component of the drift computed at recenter at the position of the particle integrated in time. So I'm just rewriting the thing that was before, just taking component 1. Okay, and then we care about the variance of this integral here, and it's a simple computation to see that if you look at the second moment of the variance of this integral, and you look at the Laplace transform with respect to time, there are two lines of computation, and then it turns out that this is given by prefactor 2 over lambda squared times the expectation of this random variable phi times the inverse of the generator lambda minus L inverse times phi. This is an inequality. This is not a bound. This is exactly, but here you have the full generator. It's not just a symmetric part. Here you just have to use the Markov property and stationarity to use translation invariance in time. There is nothing more, and then you do an integral of the exponential of something.
Sorry, what is the difference between omega and omega 1?
Yes. No, this is terrible notation. No, okay. What I mean here, yes. Okay, omega 1 means it's omega 1 of 0 simply means you look at your vector field component 1 computed at the origin. Okay, in this integral it appears but computed. Okay, yeah. Why computed at the origin? Because I'm recentering the field at the position of the particle. Okay, so this is what I'm doing here.
Thank
now
you.
here I just mean I look at this function which is omega 1 of 0. I can see it as a random function. So actually the omega in this formula is like the point in the probability space. Sorry about that. So you take expectation with respect to the law of the environment of this function, which is just the field component 1 at the origin times the inverse of the generator times the same thing. Yeah, so this omega here is a bit confusing. Okay, I hope this is better. So the point is that we have to study this expectation, but the difficulty is that it involves the inverse of the generator of this process. Now, on the other hand, what helps is that the stationary measure is Gaussian. So, and then what one can do is to, when you have a Gaussian measure, you can decompose your any L2 function in your Gaussian measure in term as a Wiener-Chaos decomposition. So you just decompose orthogonally your L2 with respect to the Gaussian measure into subspaces, each of which is generated by is spanned by the Hermite polynomials of order n. I won't say more about this, but this I hope it's known to most of you. So you can decompose your L2 with respect to P as in an orthogonal decomposition. Each subspace is generated by the order n Wick products, or yeah. Okay, and I call Hn these subspaces. Now, what is one can check looking at the generator of the process is that the symmetric part of the generator acting on the nth component of this decomposition leaves it invariant. If it acts on a random variable in the nth chaos, it spits out a random variable in the same chaos, while the antisymmetric part is not diagonal in the chaos. So there is a part which we call A+, which increases the order of the chaos. It's like a creation operator, and the A- part decreases the order of the chaos. So this is to say that what makes the thing complicated is that this generator is not diagonal in this chaos decomposition. Otherwise, things would be easy. The symmetric part is actually the symmetric part of the generator acts very simply in the chaos. It's just multiply in momentum space. Simply, it's a Laplacian. It multiplies by k squared. It's super simple. But the antisymmetric part mixes up all the Fourier component and mixes up all the chaoses. So that's why it's not easy we cannot invert generator. So, okay, so, right, so what can one do? Well, one thing one could do is to proceed variationally. So we have to compute the inverse, this matrix element of the inverse generator between two functions phi, which was, okay, there was a different script phi before. One can write a variational problem with variational formula for this, of this second line. I mean, it's not totally obvious if you have not seen it before, but it's true. It's a supremum over L2 functions of sum of 3 terms, which involve the symmetric and the antisymmetric part of the generator. Okay, so this is the fact of linear algebra. And now one could say, okay, now we have to compute this thing. Well, we have a variational principle, and this is actually what the Todt and Valco used. Using a clever test function, which is the first Wiener chaos, they managed to get a log lower bound, because it's a soup, so you can get lower bounds. On the other hand, to get the upper bound, they just drop this third term, which is negative. If you drop this, then you can compute exactly the soup, and then you get the log upper bound. And now one would like to, okay, maybe one procedure would be to find better trial states to get better lower bounds, but actually this we did not manage to do. And actually we were stuck for some time with this variational expression. We are still not able to prove our theorem using the variational expression. We had to do something different. And this something different is what I will not manage to say, but maybe I actually, since I knew I would not manage, I left one blank page where I tried just to summarize in writing what we do. Okay, so we have to compute in principle this phi. Oops. Okay, we have to compute this, and this phi is in the first chaos. So ideally, we would like to solve the equation to find okay. Ideally, we would like to solve this equation to find some f that solves this equation. At this point, we just plug this. Then at this point, this thing is simply equal to f times phi. I mean, if we are able to solve the equation. Now, the difficulty of this is that this is an infinite dimensional. It's linear in a sense, but it's infinite dimensional. And what you can do is to project it on all the chaos components. And now, so f will have component in each chaos, in each Wiener chaos, even though phi 1 has only component in the first chaos. The idea is to write the equation for each Wiener chaos, and since in L there is a term that lowers the chaos and a term that raises the chaos, all these equations will be coupled. But ideally, you can solve them one by one, iteratively, starting at plus infinity, which of course you cannot do, so you have to do some truncation, etc., etc. But ideally, you start at plus infinity, and then once you solve the equation at plus infinity, go to plus infinity minus 1, etc., and go down up to 1. Okay, so this, of course, there is a way to do this rigorously. And what comes out is that in the end, the component 1 of f is simply given by lambda minus L0 plus some h infinity inverse applied to phi, where this h infinity is an operator, or is a function on our L2 space that is defined inductively. This is because of this infinity. It's defined inductively by the equation hn equal a plus star lambda minus L0 plus hn minus 1 inverse a plus. And you start from, say, h0 is 0. Okay, so there is an iterative definition of certain operators that you have to run for an infinite time, so to speak. And in the end, the thing we care about is this is to compute this. And actually, technically, the main, and this will be the last thing I say. Technically, the core of the procedure is to prove that these operators here behave like L0 itself times the square root of the log of L0. Okay, so this is really the hard part to prove. I will not tell you how to do it. It's done inductively. Since these operators are defined inductively, you prove upper bounds for the first and then lower bound for the next, and then blah blah blah, and then you. Okay, this is really the core of the proof. But yeah. Okay, so let me conclude since yeah. Okay, so the take-home message is that in this business there are two universality classes, the so-called universality class of the two-dimensional ASEP, where you have this log to the 2/3 corrections, where this, at least for ASEP, this is proven by Yao. And the other universality class, let me call it universality class of two-dimensional fluids. I mean, this is my choice of name, where one predicts square root log t corrections, and this is the first case where we can prove a result like this for the second class. And I mean, there are many other questions, in particular, okay, going beyond somehow second moments. Can one, by rescaling the process slightly different than diffusively, can one get a limit process? We have some conjectures that the limit process will be Gaussian once you take into account these log corrections, but it is still open. And yeah, I'm a bit over time, so thanks.
Thank you very much.
Thanks.
Thank you very much for this very enlightening talk. Any questions? May I ask? Sorry.
No, you started, bro. I'll go after you.
Okay, may I ask just on the heuristic level, something was confusing me. You said that there is a tracer particle in hard disks, that would give you square root log t. This was in the fluids. But you also said that the ASEP, which is symmetric, doesn't give you any correction. And somehow, heuristically, they're very similar, because here there are particles moving with exclusion, and here also. Just one is.
No, but no, it's Yeah. No, it's because somehow there is positions and velocity in this gas model. It's not like okay. When I mentioned that there is a lattice gas version of this fluid dynamics where log T is known, actually this lattice fluid dynamics is a model where you associate to every particle a position and a velocity. And then these particles proceed with the drift which is given by the velocity, and then with the heat. So the fact that you have position and velocity is essential.
Yes, I see. Okay, so that's how it's different from ASEP.
Yes, exactly.
Okay. Yeah, Evyatar, you wanted to ask?
Yeah, so kind of surprised that there are only two classes. Is it clear that you cannot take any parameter between 1/2 and 2/3 and build a field, something that
no, I mean it's not no, it's I cannot exclude it.
So the claim is about the kind of the known examples that people played with, not that you cannot construct one, or is it a stronger claim?
Well, when you start playing with this operator, yeah, I don't have a theorem saying there is no other class, but when you start playing with these operators H, you will see that what matters, already you see after one iteration, is whether at the next stage the correction you have is rotational invariant or where it is not. So I cannot conclude that you can cook up something with exponent that is in between, but it seems that really, so for instance, in the paper by Tolt and Valco, they actually looked at, remember we had this Brownian self-repelling Brownian diffusion. They actually look at two versions, one which is the one I gave, and one where only in one direction you have this local time drift or local time x only in one direction. And then in that case, they found that 2/3, at least heuristically, and in the other case they find 1/2. So I would say that for natural models you find one of these two, but I might be wrong. Yes.
I can take the differential equation, which is the drift away from the local time, which is rotation invariant, plus some fields, like something like you did with the GFF. Right? Then you might get two effects, and maybe if you give parameters between them.
Yeah, but
so then your operator.
Okay, I think if I just sum the two effects, one of them will win, the stronger one. But what one could imagine is that you are in an asymmetric situation, and you put also okay, no, maybe you're in an isotropic situation, plus you put in a little bit of asymmetry, but with a parameter that tunes it to 0 in some way, so that the two things balance somehow to give some non-trivial exponent. This is conceivable, but yeah, it is possible. Yes.
Very, very good talk. Thank you.
Thanks.
Okay.
More questions? Okay, if not, let us thank Fabio again.
Thank you again. Thanks.
We can stop the recording.